Okay, so in this video we want to look at the graph called the rectangular hyperbola. So the curve that is produced by the rule y equals 1 on x, which is sometimes called a reciprocal function, because it's the 1 on x is the reciprocal of x. The curve produced by that rule is called a rectangular hyperbola, and we often just refer to this particular shape as a hyperbola. It's a rectangular hyperbola. Actually, I'll come back to that because we need to talk about what we call some of the things before that. So here's the graph of y equals 1 on x. Okay, you could plot out a table of values to work that out. So when x equals 1, y will be 1 over 1, which is 1. So we go through the point 1, 1. When x equals 2, y equals 1 over 2, which is 1 half. So we go through the point 2, 1 half. This is 1, 1. When x equals 3, y equals 1/3. So it's 3, 1/3. This is 4, 1/4. This is going to be 5, 1/5. So what we see is as x gets bigger and bigger and bigger, the y value is getting smaller and smaller and smaller. However, even when we get to the point when x is 1 billion and y is 1 over 1 billion, that's still a very, very tiny number, but it's still positive and it still doesn't equal 0. So what we find is our graph is getting closer and closer and closer to 0 as x gets bigger and bigger and bigger. We see the same thing happening for the negatives. So when x equals -1, y equals 1 divided by -1, which is also -1. When x equals -2, y is 1 divided by -2, which is -1 half. This is -3, -1/3. This is -4, -1/4. This is -5, -1/5. Okay, and again, as we get more and more negative, even if we're at, negative 100,000, 1 over 100,000 is a very, very, 1 over negative 100,000 is a very, very small negative number, but it's still not 0. So as we head out this way, the graph is going to get closer and closer and closer to that x-axis, but it's never actually going to reach it. We call that horizontal line along the x-axis an asymptote, okay? An asymptote, here the word is written here, an asymptote is a line that the graph approaches but never actually reaches. Okay, so we're getting closer and closer and closer to that line. When we sketch a graph with an asymptote, we want to make sure that our sketch reflects the fact that we understand what the asymptote is. So that is, we want our graph to get closer to the x-axis without ever actually touching it, without crossing over it, without also ever veering away from it accidentally, so you can't sort of flick out at the end here, and also without becoming too parallel to it. Okay, so when you draw your hyperbola, you want to be really careful about drawing the hyperbola where it just becomes parallel. Okay, and these are essentially parallel lines. You want to make sure that it is approaching, getting closer to. Okay, this also means it's important for you to think about when you draw your axes. So don't draw a really long wide x-axis and then draw your hyperbola, quite close to the x-axis, because it's going to be impossible to show you continuing to getting closer to it without actually touching it at the end. So don't draw it that far along. I'm just trying to change just draw it up to, here, where you can see that hyperbola shape. So it's about being strategic about being strategic about how you draw it as well. That, and let's get the cursor back. Okay, so this is our graph shape. Oh, the other thing we haven't looked at is when we're between 0 and 1. So let's imagine when x equals 1 half, y equals 1 divided by 1 half, which is 1 times by 2 over 1, so that's 2. When x equals a half, y equals 2. When x equals 1/3, y will equal 3. Dividing by a third is multiplying by 3. When x equals 1/4, y will equal 4. When x equals 1/5, y will equal 5. And so we've got the same thing happening up here. The graph is getting closer and closer and closer to this y-axis, but it's never actually going to reach the y-axis, and the same happening as we head down this way. So the y-axis is also an asymptote. Okay, so an asymptote, as I've said here, is a line that the graph approaches without ever actually reaching it. It's the limiting value of the graph. Okay, and we can see that y equals 1 on x has asymptotes at y equals 0, which is the equation of the x-axis, and at x equals 0, which is the equation of the y-axis. Okay. As I said, your sketch should indicate your understanding of what an asymptote is, so don't touch or cross or veer away from or run parallel to it. As with all graphs, any x and y intercepts should always be labelled, and if there are no intercepts, at least one point should be labelled on the graph, as well as the asymptotes. When we're drawing a hyperbola, we should always have our asymptotes labelled. I'm going to add that on here. So for hyperbolas, as with all graphs, any x and y intercepts should always be labelled, and asymptotes for the hyperbola. And when we label an asymptote, we draw it as a straight dashed line and label it with their equation. The only time we wouldn't do that is if the asymptote is actually on an axis. We wouldn't label it separately. Okay, we would just label our x and y axes as usual. If there are, as I said, if there are no intercepts, although there won't be no intercepts for the hyperbola, it will always, unless it's, this one we've got here is a perfect example of a hyperbola with no intercepts. So in which case we would want to label the graph as, label at least one point on the graph. 1, 1 would probably be a sensible, easy point to label. Because with no intercepts, we haven't got enough information to tell. We can tell the graph hasn't been translated because the asymptotes haven't moved, but there's no information to tell us about the dilation of the graph. Okay, so is this 0.11 or 12 or 15? So making sure you've got a point on the graph that shows that. Okay, so in the previous section we learned about the effects of transformations, both on the graph and on the equation of a function. So we learnt that when we're dilating by a factor of a from the x-axis, we get the equation is multiplied by a, so a times f of x. Now, if our function is 1 on x, as it is in this case, when we do a times f of x, that's going to be a times 1 on x, which we would write as a over x. So when we have the equation y equals a over x, that's the graph of 1 on x, the hyperbola, dilated by a factor of a from the x-axis. When we reflect in the x-axis, we multiply the whole function by -1. So in the case of the hyperbola, if the function is 1 on x, it's -1 times 1 on x, which we would just write as -1 on x. So that would be a reflection in the x-axis if we have -1 on x. If we translate to the right by h units, we replace the x in our function with x minus h. Okay, so our equation is going to become y equals 1 over, and instead of 1 over x, it is now 1 over x minus h. That is the translation to the right by h units. And if we translate up by k units, we add the k on at the end of the function. So we keep our function, which is 1 on x, and we add k on to that separately. Okay, so we want to clearly make the distinction between that being a translation up, left or right, and this being a translation up or down. Okay, and then finally we can combine all of those transformations together. The dilations and reflections from the a value, if it's negative it'll be reflected, otherwise just dilation, translation left or right, and translation up or down would all combine together in the form of a over x minus h plus k. Okay, so dilation by a factor of a, and if it's negative, reflection in the x-axis, translation left or right. Okay, if it's minus it goes right, if it's plus it goes left, and translation up or down. If it's minus it goes down, if it's plus it goes up. Okay, so we want to be able to look at a function and identify what transformations are happening, and therefore allow us to sketch the graph. The key thing to note here is the two most important transformations to think about first are going to be the translation to the right, because if you take this shape and translate it to the right, this asymptote that's here is going to move somewhere over here to the right. Okay, and so you're actually going to change your asymptote, your vertical asymptote, when you translate the graph left or right. Your horizontal asymptote will change when you translate the graph up or down. Okay, and as I said, the minute it's not the x-axis, we want a straight dashed line labelled with equation. So this is going to translate, so horizontal asymptote moves up by h units, so that means its equation would be x equals h, sorry, not up, it's a translation left to right, moves right by h, which means the equation of it will be x equals h, and in this instance the vertical asymptote, sorry, so it's not the horizontal one that moves if we're going left and right, it's the vertical one that moves. Vertical asymptote moves to the right by h, so it becomes x equals h instead of x equals 0. If we translate up or down, the horizontal asymptote moves up by k, and so its equation now becomes y equals k. So you want to think about, in order to draw the hyperbola, the asymptotes are essential structure for the shape. You must draw them in first, and then you can draw your shape around it. Okay, so let's think about this particular equation. Okay, so we've got y equals negative 3 on x. So the negative is the reflection in the x-axis. So our shape is going to be reflected in the x-axis, which means that instead of the hyperbola being up here and down here, the hyperbola is going to be here and here. Actually, before we get into drawing these graphs, let me just pause and go across to a graphing program, and we'll just have a play around with these transformations first. Okay, so here's the graph of y equals a over x minus h plus k. At the moment, a is 1, h is 0, and k is 0, so this is just y equals 1 on x. Okay, so what we see here is as we increase the value of a, sorry, hold on a second. As we increase the value of a, we're dilating away from the x-axis by, in this case, a factor of 7. So you can see that the original hyperbola went through 1, 1, and now it goes through 1, 7. It went through negative 1, and it now goes through negative 1, negative 7. So we've dilated the graph away from the x-axis by a factor of 7. If we were to make a smaller, so a is 0.5, we've dilated the graph from the x-axis by a factor of 0.5, so all the y values have been halved. So instead of going through 1, 1, we go through 1, 1 half. If a becomes 0, it's not a hyperbola at all, it's just y equals 0, so that's a bit trivial. But then if a is negative, the graph is reflected in the x-axis. So here a is negative 1. We see now our hyperbola, instead of going through 1, 1, now goes through 1, negative 1. And now we've got a branch of the graph down here in the bottom right quadrant. And similarly, the point that was at negative 1, negative 1 is now at negative 1, positive 1. And we've got a branch up here in the top left quadrant. Okay, so then we can reflect and dilate, so both stretching away from the x-axis and reflecting in the x-axis. Okay, let's go back to a equals 1. If we now have a look at h, h translates the graph left or right. So as I make h bigger, oh sorry, let me just tidy that up quickly. Okay, let's try that again. So if we've got a over x minus h plus k, we know if we make h bigger, just because of the way I've set this up, so if h is 1, that's 1 over x minus 1, so the graph has gone to the right by 1, and we see that vertical asymptote is also going to move to the right if we translate to the right. So now we have h is 4, so we have y equals 1 on x minus 4. If h were to be a negative value, so negative 1, we now have 1 over x minus minus 1, so that's 1 over x plus 1, and the graph has gone to the left. Okay, oops, sorry. So, 1 over x plus 4 is the hyperbola translated to the left by 4, and that vertical asymptote is going to translate along with it. If we change k, increasing the value of k will translate the graph up by k units. So here we have the graph of 1 on x plus 3, and the asymptote has also moved up. It now has an equation of y equals 3. Similarly, if we translate down, the asymptote has now moved down by 4 units. It has an equation of y equals negative 4. And we see we've got an x-intercept that would need to be calculated if we were drawing that on the paper. If we translate the graph left or right, we create a y-intercept that we need to calculate if we're going to draw it on paper. And obviously we can have combinations. We can go to the right by 2. Oops. Sorry, let me fix that. We go to the right by 2. We can go up by 1. And we can also add in a bit of a dilation. And we can draw our hyperbola. So we want to be able to think about those combinations of transformations. Let's just go back to the notes and the example. Okay, so having looked at that, let's resume back to talking about this particular graph, y equals negative 3 on x. So we've established the negative is the reflection in the x-axis, which means the graph is going to be in the top left and bottom right quadrants. And the 3 is a dilation by a factor of 3 from the x-axis. Okay, so that's going to stretch the graph. So our graph is going to be in the top left and bottom right quadrants. With no translations, the asymptotes are still the x and y axes. We're going to need to, because the asymptotes are the x and y axes, we don't have any axis intercepts, and so we need to mark a point on the graph. So any point you want, when x equals 1, for example, y would equal negative 3 over 1, which is negative 3. So that's the point 1, negative 3. You might also choose to do when x is negative 1. Sometimes it's good to have a point on both branches of the hyperbola. So y would be negative 3 on negative 1, which is positive 3. So that's the point negative 1, 3. So it might be a good idea just to plot those points, just to help a bit with shape, give us a bit of a sense. We want to make sure that our graph approaches our asymptote without veered away a little bit there. Let's stay headed towards that. We also want to try and aim for a bit of symmetry if we can, but that's going to be our graph. So we want to label, given we've got no axis intercepts, we need to label at least one point. You don't need both, but I do think it's nice sometimes to have the point on both branches. It also indicates the symmetry. Okay, let's have a look at example 2. Sketch the graph of y equals 1 on x plus 2 plus 5. Okay, so we've got this plus 2 in here and this plus 5 out here. So the plus 2 is going to be a translation to the left when we're adding by 2 units, okay? And then the second value there, the plus 5, which I've highlighted in blue, is going to be a translation up by 5 units, okay? So if we go to the left by 2, that means we have an asymptote. Instead of it being the vertical asymptote with equation x equals 0, it's now a vertical asymptote with equation x equals negative 2. And up by 5, instead of having a horizontal asymptote at y equals 0, we now have a horizontal asymptote at y equals 5. So we're going to start by drawing those in. They give us the structure in which to draw our graph, and then we can calculate any intercepts that we might need. So let's have a think about what's happening here. So we're going to have negative 2 and 5. So straight dashed line labelled with its equation. Okay, so our hyperbola is going to be up here and here. So we're going to cross the y-axis somewhere here and the x-axis somewhere here. So let's calculate those points. So our y-intercept will be about letting x equal 0. So it's y equals 1 over 2 plus 5. So that's 5.5. Or as a mixed number, sorry, as an improper fraction, 5 is 10 on 2, so 1 on 2 plus 10 on 2 is 11 on 2, or 5.5, so it's going to be reasonably close to my asymptote there. I'm not going to mark the point, it's hard to hit it, just draw the shape in and then mark it when you've got it. Then we're going to have our x-intercept, we let y equal 0, plus 5, so we're going to take away 5. I'm going to multiply by x plus 2. You can expand out that bracket if you want, or you can just divide by negative 5 first. So it's negative 1/5. So x equals negative 2 minus 1/5. Negative 2 is 10/5. So negative 10/5 minus 1/5 is negative 11/5. But it's negative 2 minus 1/5, so it's sort of negative 3 4/5. So it's just going to be a fifth past here. So we want to hit quite close to the vertical asymptote, not quite as close to the horizontal asymptote. It's getting, my mum is getting a little bit parallel to the asymptote up there, so just be a bit careful about that, but it's not too bad. Alright, so this is going to be the point 0, 11 on 2. And this is the point negative 11 on 5, 0. So we've got asymptotes drawn as straight dashed lines labelled with equations. We've got all axis intercepts labelled, and we've got our x and our y-axis with our hyperbola drawn in. Okay, example 3. Sketch the graph of y equals negative 1 on x minus 4. Okay, so again, there's two transformations we need to think about here. We've got the negative out the front, okay, and that negative out the front is going to be a dilation, sorry, not a dilation, a reflection in the x-axis. And then that negative 4 underneath the fraction is a translation left or right, and because it's a subtraction, we are going to the right by 4. So this is a translation to the right by 4. Okay, so the reflection in the x-axis means our graph is going to be in the bottom right and top left quadrants. Translation to the right by 4 means that our asymptote, our vertical asymptote, is going to be at x equals 4. There's been no translation up or down, and so our horizontal asymptote is going to be still at y equals 0. Okay, so you want to think about where those asymptotes are going to be. So y equals 0 needs to be in the middle for our shape. We sort of want x equals 4 to be in the middle, so let's draw our y-axis over there so that we can draw in x equals 4. Okay. Now, the graph we've just talked about is going to be in these two quadrants, so we're not going to get any x-intercept. This is where you want to think about it before you do your calculations. The graph doesn't cross the x-axis. The x-axis is an asymptote, but we will get a y-intercept somewhere up here, a positive y-intercept. So let's calculate that. Y-intercept, y is going to be negative 1 on 0 minus 4, so it's negative 1 on negative 4, so the negatives will cancel each other out. It's just going to be positive 1/4. So we just want to draw in our hyperbola shape, 0, 1/4, and draw it in over here as well. Again, it can be nice to put a point on both branches, so if you wanted to do so you could. The symmetric point would be at 8, negative 1/4, be symmetrically opposite to this one, okay? Or you could just plug in a number, so when x equals 5, for example, when x equals 5, you'd have negative 1 over 5 minus 1. Sorry, negative 1 over 5 minus 4. So if this was 5, your denominator would be 1. So it's just going to be negative 1. So if you want, you could mark that in. But you don't need to. Your asymptotes and one other point are enough information for the equation of the hyperbola. The horizontal asymptote is the x-axis, so we don't need to label it with its equation, but its equation is y equals 0. Vertical asymptote, straight dashed line labelled with its equation. Okay, and example 4. Sorry, I read that 18 at the same time. Okay, I'm just seeing how many we've got. So 6. Example 4. Sketch the graph of y equals 1 over 3x minus 18. Now this is a bit tricky here. I want to think about y equals 1 over 3x as being 1/3 times 1 on x. Take away 18. So this is essentially our a value, a times f of x minus h plus or minus k, okay? And then this is our k value here. So what we have here is dilation by a factor of 1/3 from the x-axis. So that's not really going to change how we draw our graph. It's just technically going to be closer to the axis, but that'll come into it when we calculate points. The minus 18 is a translation down by 18 units, which means that our horizontal asymptote is going to be at y equals negative 18. No translation left or right means that our vertical asymptote will still be at the y-axis, x equals 0. So again, think about where those asymptotes are when you draw your axes. So you're going to want a big negative y-axis. So we'll draw our x-axis right up here. Okay. So we want y equals negative 18, and the y-axis is the vertical asymptote. No reflection, so it's going to be up here and down here, which means we'll cross the x-axis there. We won't cross the y-axis because that's an asymptote, so we just want to calculate that x-intercept. In fact, I'm going to make my graph a bit narrower because I'm probably, I don't know, I'll just calculate it out here. So my x-intercept is letting y equal 0. I'm going to add 18 to both sides. I'm going to multiply both sides by 3x. 18 times 3 10 times 3 is 30, and 8 times 3 is 24, so that's going to be 54x equals 1, and so x equals 1 on 54, so it's a very small x-intercept. Just going to draw in my hyperbola. So this point here is 1 on 54, 0. Don't have any y-intercept, we've got our asymptotes labelled with their equation, apart from the y-axis. Alright, finally, sketch the graph of, sorry, no, there was 6, wasn't there? Example 5, sketch the graph of y equals 1 on 2x plus 1, showing all important features. Now again, this is a bit mean in terms of its format, but there's some like this in the exercise, so I want to have a look at it. So we don't normally have a number multiplying under here, so we want to get that out of there, okay? So I want to be able to think about this as being 1 on 2 times x plus a half, okay? Which I can think about as being half times 1 on x plus a half. Okay, so this is our a value out the front here, that's our dilation from the x-axis, and then this is our translation left and right, okay? So the a value is a dilation by a factor of 1/2 from the x-axis. Okay, so it's going to get squashed down, and that plus 1/2 in the denominator of the fraction is a translation to the left, because we're adding to the left by 1/2 units. So that means we're going to have an asymptote, a vertical asymptote when x equals -1/2. And there's no translation up or down, so the horizontal asymptote is still at y equals 0. Okay, so let's think about that. Horizontal asymptote at x equals -1/2. Vertical asymptote at x equals -1/2. Horizontal asymptote is just the x-axis. So no reflection, just a bit of dilation, so the graph's going to cross the y-axis somewhere there, and it won't cross the x-axis because the x-axis is an asymptote. So let's just work out the y-intercept. We let x equal 0. Let's go back to the original equation. So y equals 1 over 2 times 0 plus 1. So it's just 1 on 1, which is 1. So we've got a y-intercept at 1. So 0, 1. Let's draw in our hyperbola and draw it in over here as well. Once again, you can calculate another point if you want. You could look at when x equals -1, for example, and plot a point somewhere down here, but it's not required. Both asymptotes, we've got one asymptote here and the other is the x-axis, y equals 0, and one additional point is enough. Okay, so the final example here is when we want to sketch something of this form. Now this actually is a hyperbola, but it's not in the nice standard form where we can see the transformations. So we want to focus on rewriting it in a different form. So the first part of this question is asking us to show that this expression is the same as this expression. And so then when we're trying to sketch the graph of y equals this, we know that that's the same as sketching the graph of y equals this, which is going to be easier to sketch. We can see the reflection, the dilation, the translation left or right, and another colour, the translation up or down. Okay. So first things first though is to show that this thing is equal to this thing. Okay. Now when we do a show that, this is such an important instruction in methods. Okay. You'll see this a lot. And it's important that you understand that you can't use what you're trying to show it. So what we don't want to do is start by assuming these are equal and subtracting 5 from both sides and multiplying both sides by -1 and ending up with 0 equals 0. That's true, but it's meaningless. What you need to do if you're trying to show that one algebraic expression is equal to another one is you start with the left-hand side and manipulate it to turn it into the right-hand side, or you start with the right-hand side and you manipulate it until it looks like the left-hand side. You don't meet them halfway, okay? You don't play around with the left and play around with the right and try and get them to both equal the same thing at some point. So I'm going to start with the left-hand side. I'll have a look at how you would do it the other way. The left-hand side is 5x plus 3 over x plus 1. Now the advantage of show that is we know what we're aiming for. And the key thing that I'm noticing here is I'm aiming for a fraction that doesn't have any x's in the numerator. So I need to be able to cancel x out of the numerator. And the only way that that can happen is if it will cancel down with the denominator, and the denominator is x plus 1. And so therefore, I need to have an x plus 1 in the numerator of this fraction in order to be able to at some point cancel down the x's out of the numerator with the denominator. So I just write the denominator in the numerator because that's what I want. And then I work around it. So if this has got a 5x up here, the only way I'm going to get a 5x here is if there's 5 outside of that bracket. Now when there's 5 outside of that bracket, if I expand that bracket out, I get 5x plus 5, but I want plus 3 here, and so therefore if I take away 2, these are now the same. 5 times x plus 1 take away 2 is 5x plus 3. So they're the same thing. We're not trying to make them different, we want them to be equal. But what this allows me to do is split this into two fractions. There's one fraction and there's the other fraction. Okay, this is the same as 5 times x plus 1 over x plus 1, take away 2 over x plus 1. The x plus 1s will cancel out, and so it's 5 take away 2 over x plus 1, which is not quite the form I was asked to show, so let's be really explicit. That's the same as negative 2 over x plus 1 plus 5, which is the right-hand side. And so I have shown that the left-hand side equals the right-hand side. The alternative would have been to start with the right-hand side, okay, which was negative 2 over x plus 1 plus 5, and get it to equal the left-hand side. So you would have needed a common denominator, plus. If we want to write this over x plus 1, we need to multiply the numerator by x plus 1, so we get that. And now we can combine them together. And so we get negative 2 plus 5x plus 5 over x plus 1, which is 5x, and we've got negative 2 plus 5, which is plus 3 over x plus 1, which is the left-hand side. Okay. One or the other of those two things, not a combination of the two. Okay. Personally, this is a good strategy to practice. It's something you will need to be able to do next year. Those who do specialist, there's something called partial fractions, which is quite similar to this, although you don't need anything as formal as partial fractions here. Just start by writing the denominator in the numerator and then work out what needs to go around it to still keep it the same. Okay, so we've done the first part of the question, which is to show that these two things are equal. Okay, and hence, so use what you've just shown to sketch the graph. So as we said, if we know we're trying to sketch y equals 5x plus 3 over x plus 1, that's the same as us sketching negative 2 over x plus 1 plus 5. And as I said, we can think about our reflection in the x-axis, our dilation by factor of 2 from the x-axis, our translation to the left by 1, and our translation up by 5. And then we can sketch the graph. Sorry, I've used a lot of my space in the algebra. So we've got reflection in the x-axis, so the graph shape is going to be in these two quadrants. Okay, we've got dilation by factor of 2 from the x-axis, so that's just going to stretch it. It'll just change where the points are, so we don't need to think about that in the drawing. We've got a translation to the left by 1 unit, and we've got a translation up by 5 units. So this means we've got an asymptote at x equals negative 1. This means we've got an asymptote at y equals 5. Okay. Okay. So they give us the structure, and then let's work out whether we need to calculate any intercepts. So x equals negative 1 and y equals 5. X equals negative 1. So you don't need to use the exact same scale on both the x and y axes. Just thinking about, obviously, I want my 5 to be bigger than my negative 1, etc. Okay, so I've got my asymptotes labelled in. My graph has been reflected. Oops, sorry, let's get rid of that. So it's in the bottom left and top right quadrants. So we're going to be crossing through x and y axes somewhere down here. Now it could be down there, like I just drew, or it could actually be here. So we need to actually calculate things before we draw it in. We won't cross any axes up here. So let's calculate our various intercepts. So our y-intercept, we let x equal 0. It might be easier to go into this original version of the equation here, because when we let x equal 0 there, we're just going to get 3 over 1, which is 3. It's a bit easier than that one. So again, be flexible. These are the same thing. Use whichever one is easiest. However, when I'm finding the x-intercept, which is letting y equal 0, to solve for x, I'm going to use the version where we've only got one x. This is going to be more complicated if we've got two x's. So our x-intercept is going to be 0 equals negative 2 on x plus 1 plus 5. I'm going to add this whole fraction to the other side to get rid of that negative. So it is 2 on x plus 1 equals 5. I'm going to multiply both sides by x plus 1. So we get 2 equals 5 times x plus 1. Now you can expand out first, or you can divide by 5 first, whichever you prefer. Last time I divided by 5, so let's perhaps expand out this time. Let's take away 5 from both sides, so negative 3 equals 5x, and dividing both sides by 5 is negative 3/5. Okay, so we have indeed found that our y-intercept is at 3, which is about here. You do want to make sure that it's consistent. If you've got y equals 5 here, you don't want 3 to be down here. Okay, it's got to be past halfway. So it's going to be around about there, and then negative 3/5 is past halfway here as well. Okay, so we want to draw in our graph. Okay, we've got 0, 3 for our y-intercept. We've got negative 3/5, 0 for our x-intercept. And then don't forget the other part of the hyperbola. You could calculate a point up there if you wanted. X-axis, y-axis, asymptotes labelled with equations, and all axis intercepts are labelled. Okay, so the work for today is here from exercise 4a, just practicing sketching some graphs of hyperbolas.